A logical vector is an expression in MATLAB that produces a vector-valued output where each entry is a logical scalar. Logical vectors come in two flavors. Either they're called logical column vectors, which are a size m by 1, having m rows and 1 column, or what we call logical row vectors that are of size 1 by n, having 1 row and n columns. In either situation, whether we're looking at a logical column vector or a logical row vector, each individual entry of such vectors are stored as logical scalars. Remember, that means that MATLAB assigns the individual entry values to be a 1 by 1 logical output, where the individual entry values are either stored as logical 1, representing a truth value of true, or logical 0, representing a truth value of false. In other words, logical vectors are one-dimensional arrays, either column vectors or row vectors, containing a number of entries, each of which is a logical scalar, has the value of either 1s or 0s. So logical vectors are a set of entries that are either logical 0 or logical 1, corresponding to either false or true, respectively. Let's write some code to actually test out what a logical vector is. To do this, let's remind ourselves of what we call the logical function in MATLAB. So we type help logical. We see that logical converts numeric values to logical values. And in order to call this function, we actually type in logical, the function name, and then input an array called x. When we do logical x, this converts the elements of the array x into logicals. Moreover, we notice that any non-zero real value input of the array x is converted into logical 1, while 0 values in the array x become logical 0. There's something about complex values and NaNs, this means not a number, and those are not converted into logicals. We'll talk more about that in more advanced videos. The point of this, though, is that when we call the logical function on an array x, MATLAB will output what we call a logical array. Each entry in the logical array will be 1 if the corresponding entry of x is a finite numeric entry, or will be 0 if the corresponding entry of x is a 0 numeric entry. Let's take a look at how to produce logical row vectors using the logical function. To do that, let's write some code to create this vector x and store it in memory. Notice that x is a row vector with 10 entries, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The odd entries, so entry 1, 3, 5, 7, and 9 are all zeros. And then the even entries, entry 2, 4, 6, 8, 10, those entries all represent power of 2s. Let's go ahead and write the code to create that. So we'll go ahead and set x equal to the vector of all zeros. How big is that vector? It's a 1 by 10. Then what we want to do is create powers of 2s, and particularly notice that we want 5 separate power of 2s. So we're going to create 2 times the vector of 1s, and this will be a 1 by 5 vector. Then what we want to do is take the vector of 2s and take individual powers. Notice we said that we wanted the powers to start, let's see. The first power of 2 is 2 to the 0, since 2 to the 0 is 1. The second power of 2 is 2 to the 1. Third power is 2 to the 2, 2 to the 3, 2 to the 4. So I need to take the individual powers of 2, start at 0, go up by 1, and go to 4. That should get me the vector 1, 2, 4, 8, 16. But notice I want to place those in the even entries of my vector x. Well, I know from a previous video that I can actually refer to specialized entries in my vector using colon notation. So specifically, we're going to take this vector, which is the one that we wanted, and then we're going to store it in the appropriate places in x. Well, which places do we want to store? We want to store starting at the second entry of x. We're going to go up by 2s and go all the way to the 10th entry of x, and we want to overwrite the previous values of zeros in those locations with our new values of powers of 2. Boom, baby, I got it. Look at this. My value of x stored in MATLAB is now 0, 1, 0, 2, 0, 4, 0, 8, 0, 16. That's exactly the desired value of x that I wanted from this location. Moreover, when I go to the workspace, I notice that x is a 1 by 10 numeric variable. Specifically, these are stored using the double class. So every single scalar in this row vector is stored using a 1 by 1 double scalar. The reason that this is important is now if I define a new vector, let's call it Lx for logical version of x, and let's go ahead and type in logical, the function, and input to the function the vector x. The moment that I push enter on that, MATLAB produces an output and stores that output as the logical row vector Lx. Remember, we said that logical row vectors were expressions in MATLAB that produce logical row vectors where each entry is either 1 or 0. So specifically, notice that Lx is a 1 by 10 vector, and it stores 0 everywhere where the corresponding value of x is 0. And it stores 1 everywhere where the corresponding value of x is stored using a finite numerical entry. So in this particular, 1 is non-zero, so that gets logical 1. The numeric value 2 is non-zero, so that's stored as logical value 1. 4 is non-zero, stored as numerical value 1. All the way to the last entry, 16 is a non-zero finite numerical entry, so that is stored in the corresponding logical row vector as 1. In other words, when I called logical of x, MATLAB tests, are the entries of x equal to 0, in which case store that as a logical value of 0 in the corresponding address, or are the entries numerical data that are non-zero and non-infinite, in which case convert that numerical value into a logical value 1. The final thing that I don't even want to spend much time on, but I want to show you, is that MATLAB has special treatment of things called NaNs. This is called not a number. This has to do with floating point data. We will talk about that in a future unit in this class. But the point of the matter is sometimes there are things in the numerical data class that are not assigned a number. If I actually went to call logical on this new vector x, MATLAB gets upset with me because logical cannot be called on NaNs. In other words, it's not as simple as just checking whether or not the entries of a vector are 0 or not 0. Anytime an NaN show up, we can't call the logical function on that. So specifically, if I wanted to make sure to convert x to a logical, I need to make sure that every entry in x is not NaN. Now, the moment that I do that, I can call my logical function, MATLAB doesn't complain, and it produces values 1 everywhere we have a non-zero value and 0 everywhere we have a 0 value. So in other words, when I'm calling the function logical of x, I'm telling MATLAB, please show me the places where x is 0 and non-zero. Where it's 0, please produce the value false. Where it's non-zero, please produce the value true. Store the result in a logical array of the same size. We could always check to see if a variable represents a logical row vector simply by looking at the variable name, in this case L of x. Notice that that variable is stored using the logical data class. Moreover, the size of that variable is a 1 by 10. We immediately see that that is a non-scalar variable. Scalar variables have to be 1 by 1. That is actually a row vector. So this is a logical row vector. It's a row vector, each of whose entries are either 0 or 1. Let's clear our command window and take a look at yet a second example. This time we'll create a logical column vector. Here we'll start with a vector y, which stores 1 in entry 1, 0 in entry 2, -1 in entry 3, and then that pattern repeats itself 4 times. 1, 0, -1, 1, 0, -1. 1, 0, -1. In this case, we're going to store this as a numeric variable. So notice this is a 12 by 1 column vector. Let's go ahead and initialize y having all zeros, and specifically we're going to have 12 rows and 1 column. Notice that entries 1, 4, 7, and 10 are going to be all equal to 1. So specifically, if I say y, let's go start at 1, we'll go up by 3 and go to 10. This is going to be in the first column. That's going to be 1s, and it will be a 4 by 1. So that gets me entries 1, 4, 7, and 10. Notice that entries 3, 6, 9, and 12 are also going to be some scalar multiple times 1s. So specifically, I can go back to that last call. In this case, instead of starting with entry number 1, I'm going to start with entry number 3. I'm going to go up by 3s and go to the last entry of 12. They're not populated by 1s anymore. In fact, they're populated by negative 1s, which is just negative 1 times 1. Now I have my vector y, which is a numeric vector. How do I know that's numeric vector? Because if I go over to the workspace, notice that y is a 12 by 1 column vector, has 12 rows and 1 columns, each of whose entries is stored using the numeric data class called double. Remember, we can convert numeric data into logical data by the logical function. So if I say ly equals logical of y, MATLAB is going to run through each individual entry of this vector and do a quick check. Is it a numeric 0 entry, in which case please produce the logical 0 in the same location? Is it a non-zero numeric value that is also not a NaN, in other words, that is an actual number rather than not a number? When I make this call, MATLAB encodes that data exactly as such. As a preview of coming attractions, check this out. If I actually took y and then dropped in the logical array ly, MATLAB would produce only the non-zero values of that array. That is not part of the deliverables of this particular videos, but I wanted to show you some of why we're spending some time to develop the approach to logical arrays as a tool that we're going to use in other programming projects. That leads me to the community challenge of today, which is, what are the similarities and differences between logical scalars and logical vectors? What examples do you have of situations where you would want to use only a logical scalar versus situations that you might want to use a logical vector? You can post those in the comment section below. Of course, I always welcome your comments and questions. Thank you so much for your attention. I'll see you in the next video where we describe logical matrices.